As a team leader, I was responsible for finding sponsor and technical and substantive support. Our sponsor, ProIdea, provides us full funding and contact to companies which could help us with their technical knowledge in fields in which we had no previous experience. Sponsor gave us access to workshop fully prepared to our work, for what we are really grateful.
As a team mechanic, I faced several challenges during designing rover's components. One of the toughest for me was how to make the rover able to climb half a meter high obstacles. To achieve this, we decided to use suspension based on rocker bogie system and 16 inches wheels designed to be as light and durable as possible. Every wheel is driven by its own DC motor with high ratio gearbox, providing suitable amount of torque. Big wheels of course necessitate large sizes of all other components, so it is a very hard task not to exceed the weight limit. Other curious experience for me was designing a mechanical arm. It's able now to lift up to 10 pounds, and thanks to having 6 degrees of freedom, it has a great maneuverability.
Our communication system is based on 2 transceivers for 2 frequencies. 2.4 GHz frequency is supported on rover by Ubiquiti Rocket transceiver and 2 omnidirectional antennas in MIMO standard, and modulated with direct sequence spread spectrum, and in our base station by the same transceiver and Yagi antenna. 900 MHz frequency is supported by Ubiquiti Rocket transceiver and 2 omnidirectional antennas in MIMO standard and panel antenna in our base station. On rover side, router is connected with our onboard computer and 2 transceivers. Video packets are sent on frequency 2.4 GHz and other packets with rover control or telemetry on frequency 900 MHz. Electronical project requires PCB-like protoshield but designed by us for each microcontroller with corresponding outputs and connectors for components in subsystem. For power supply subsystem, we choose LiPo packets connected to current and voltage stabilizer, fuse circuit and safe start peripheral.
I had to choose rover computing and vision hardware and layout. We have decided to use NVIDIA Jetson TK1 running Ubuntu-based operating system with CUDA-capable OpenCV support. Primary vision system are 2 twin 720p 30fps cameras suspended on gimbal-like mount on rover's antenna mast. Secondary system is low-resolution 1.3 megapixel camera mounted on rover's robotic arm. Software consists of 3 main components. First part is C#.NET Rover Control and Management application for Windows PC. Second is Node.js daemon running on rover's Jetson TK1. Daemon is responsible for streaming video and stereoscopic images, responding for commands and passing telemetry, GPS and accelerometer data. Software communicates over network via WebSocket HTTP eventing based on Socket.io library. Daemon communicates with third layer of software stack running on Arduino microcontrollers.
ARM is driven by continuous servos with incremental encoders that provide feedback for microcontrollers. We also use optical-based sensors to make positioning in Cartesian coordinate system possible. Microcontroller code contains PID controllers responsible for synchronization of joint movement. To simplify the problem of steering, we had split it to ARM with 3 rotational joints and spherical wrist. More complicated functions such as ANFIS network for arm positioning are implemented on Daemon application. Lab equipment contains sample collection tool, which is a specific drill mounted instead of a gripper, and revolving magazine for soil samples. We designed 3D printed vials which enable us to operate samples without mixing soil layers.